Hello, and welcome to Chapter 1, Section 3. We're splitting Section 3 into a couple different videos so that we can kind of make sure we learn this stuff really well. So last time we talked about finding limits using a graph or numerically by making the table. Today, I want to talk about finding limits algebraically, so no graph, no table. There's 4 general strategies that I'm going to show you. This works pretty much all the time. So the first strategy is the easiest one. It is just straight up plug it in. But this doesn't work all the time. That's why there's 4 different strategies. So plug in just means that if we have like some limit that we're trying to find, let's just say for the limit as x approaches 2 of x squared plus 5x plus 4. So plug in just means you can just plug in what the x value is and then find the limit. Graphically, what this means is there's no holes or anything like that in this graph, so you can just plug it in. So into x squared plus 5x plus 4, this, if we were to graph it out, like graphically, this would be a parabola facing upwards. On parabolas, there's no holes, there's no like weirdness to the graphs. None of the whole like 2 different values that it's approaching or anything like that we talked about last time. So if we just plug in the x equals 2 into this, we would get 2 squared plus 5 times 2 plus 4 gives us 18. So 18 would be our limit. And you can check your work by graphing this out and then seeing that at the point 2, x equals 2, the y value is 18. Okay. I'll show you another one just in case, but the whole reason why we're able to plug in is because we're not breaking any math rules. So the only reason you wouldn't be able to plug in is if you had a rational function like this, where you're dividing by something. If you ended up with like 0 on the bottom when you plugged in, then that would not be allowed. That's when you're not allowed to plug in. Or you break any other rules, like, so dividing by 0 is a rule that you can't break, taking a square root of a negative number is something you can't do. So those are the instances where you can't just plug in. So again, since we don't end up breaking the divide by 0 rule here, we end up with 6 on the bottom, which is perfectly okay. And then on top we have the 2 squared plus 5 times 2 plus 4. So we end up with 3. Cool. Plug-in is the easiest way. The second method is to factor and cancel out. So this will happen when you have something like this. If we have the limit as x approaches 2 of, let's say, x squared, minus 3x plus 2, or x minus 2. So here's an example of where we can't just plug in, because if I were to plug in x equals 2 into the bottom, I end up with 0, and that's bad. So what I'm going to do is factor first. So I'll factor the top into x minus 2, x minus 1. Which is nice because we have an x minus 2 on both the top and the bottom. So that'll cancel out, leaving us with just the x minus 1. And once I've canceled, now I don't even have fractions, and so I can just plug in and end up with 1 as my limit. Yay! I'll do another example. So let's say we had the limit as x approaches 3 of x cubed minus 27 over x minus 3. So again here, I can't plug in just because I'm going to end up with 0 on the bottom, and that's bad. But I can factor the top using the difference of cubes. Because x is cubed, 27 is a cube number, and the formula was the a squared plus ab plus b squared. If you remember from back in Algebra 2, a lot of people teach it with like SOAP, S-O-A-P, like same, opposite, always positive. Okay, once we've factored, again, stuff hopefully cancels. And then once we cancel, oops, I forgot the limit. Once we cancel, then we're left with the x squared plus 3x plus 9. And now we don't have fractions anymore. So right when we plug in, that's when we can stop writing the limit thing at the beginning. And this gives me 27. Cool. All right, one last factoring one. So if we have the limit as x approaches 9 of 9 minus x over x squared minus 81. Right now, if we plugged in the x equals 9 into the bottom, we would end up with 0 on the bottom again. So that's no good. So let's factor this out as much as possible. So the bottom can factor out into x minus 9 and x plus 9 because that's a difference of squares. And then if you look at the top and the bottom, right now there's nothing that cancels because nothing is exactly the same, but the 9 minus x kind of looks like the x minus 9. I don't know if you've seen this before, but the cool trick is to factor out a -1 out of the top. And then that way, when you take out a -1 from the x, you end up with a positive x, and when you take out a -1 from a positive 9, you end up with a -9. And look at that, now we have x minus 9s that match. So now we're taking the limit as x approaches 9 of -1 over x plus 9. And now when I plug in 9 on the bottom, it doesn't equal 0 anymore. So my final answer is going to be -1 over 18. Cool. So that's another factoring one. My third strategy is called Rationalize. You use this a lot when you have radicals in your function, because rationalizing will get rid of radicals, and that's what we're trying to simplify. Okay, so my first example, I have the limit as x approaches 0 of the square root of x plus 1 minus 1 all over x. So if I were to plug in 0 right now, I would end up with 0 on the bottom, which is not allowed. So what I want to do is to rationalize anywhere where there's radicals. When I say rationalize, I mean multiply the top and the bottom by the conjugate. So if you remember, the conjugate is when you have basically the same thing as whatever you're trying to rationalize, but you switch the sign. So conjugate is where you switch the middle sign. And so when you do this, we can FOIL out the top so that you have your square root of x plus 1 times the second square root of x plus 1. And when you multiply the same thing twice with radicals, then the radical goes away, turning this into just regular x plus 1. And then multiplying the square root of x plus 1 with the positive 1 at the end gives us plus 1 times the square root of x plus 1. Then the inside terms will multiply into minus 1 times the square root of x plus 1. And then the last terms multiply to -1. And there's still a limit here because I haven't plugged in x equals 0 yet. And then on the bottom, I'm actually not going to FOIL out anything. I'm going to leave it factored. So it's going to be the x times all that craziness. Okay, but on top, what's nice is when you rationalize, the middle term should always cancel out. That's the nice part. Because once it cancels out, then things look a lot simpler because you're not going to have radicals on top anymore. We have that x plus 1 from here, and then we have that -1 at the end, which simplifies even further because now the top's just going to be regular x. And look at that, we have an x on the bottom that we can cancel out with, leaving us with just the limit as x approaches 0 of 1 over the square root of x plus 1 plus 1. And it seems like we did a whole lot just to make it like flip itself, kind of. But now if you plug in 0 at the bottom, you're not going to end up with 0 anymore, which is nice because that's what we need. if I plug in 0 onto the bottom, I end up with the square root of 1 plus 1, which is just a half. So rationalizing, just a little bit more work here, but your answers come out nice at the end, and that's the goal. Okay, so let's do another example where we have to rationalize. And again, as you look at the function here, we have the limit as x approaches 16 of 4 minus radical x. And again, you see the radical, so that's how you know, like, I should rationalize over x minus 16. So to rationalize, we're going to multiply the top and the bottom by that conjugate. So in this case, it'll be 4 plus radical x. And we do the same thing on the top and the bottom. The reason why we want to do it on both the top and the bottom is because really, like, if you were to simplify this fraction right here really just equals 1. So you're just multiplying like the original equation by 1, which doesn't change the value of anything, and that's why we're allowed to do that. So multiplying this out, the 4 times 4 is 16. The outside and inside terms will always cancel out, so that would be a 4 root x minus 4 root x. So I'm not even going to bother writing that out anymore. And then I have the minus root x times the positive root x, which turns this into a negative x. Okay, on the bottom, oh, I keep forgetting to write my limits. Here we go. Let's just move this over a little bit, and then I can write the limit. Yeah, technically that limit's supposed to be there until you actually plug it in, and we haven't plugged in anything yet. So I have that x minus 16 from front, and then we also have that 4 plus root x. Okay, and again, I'm not going to FOIL that out or anything just because I know I want to cancel at some point, and I can kind of already see it. I have the 16 minus x here and an x minus 16 here, so I can factor out a negative 1 so that I can make them match. Now I can cancel the x minus 16, which will leave me with negative 1 on top and that 4 plus root x on the bottom after that cancels out. Cool. And now I won't end up with 0 on the bottom of the function when I plug in the x equals 16. So that'll leave me with negative 1 over 8. Cool. Okay, our last method of solving or finding limits algebraically is with complex fractions. So this just describes when you would use it. If you see a complex fraction, that's when you would use this method. So if you remember, complex fractions are when we have like fractions on top of fractions. Lovely, I know. So let's say we have the limit as x approaches 0 of 1 over x plus 5 minus 1/5 over x. See, fractions on top of fractions, kind of crazy looking. However, solving them is pretty simple. First of all, we can't plug in right now because once I plug in the x 0 for x, I end up with 0 on the bottom. So, wah wah. Okay, so to deal with complex fractions, what we want to do to get rid of complex fractions is to multiply the top and the bottom by the common denominator. So what I mean by common denominator is look for all the little fractions within your complex fraction. So like here's a little fraction, the 1 over x plus 5. The 1 over 5 is also a little fraction. So between those two little fractions, the common denominator would be 5 times x plus 5. So when you look for a common denominator, it's that least common multiple concept that we want to find. So you're basically looking for like one of everything. So we want one of the 5s, one of the x plus 5s. Okay, so when you multiply the top and the bottom by the common denominator, on top we're going to have to distribute this out to both of the fractions. But when I do that, the whole point of this is to cancel some stuff out. So that limit's still there. But when I multiply my 1 over x plus 5 times 5 times x plus 5, the x plus 5s will cancel, leaving me with just that 1 and then the 5. Then I have the minus sign, and then 1/5 times 5 times x plus 5. The 5s will cancel, leaving me with just the 1 and the x plus 5. Okay, on the bottom, I'm just going to leave this all not multiplied out. Okay, cool. Again, our goal is to always cancel out with something, because now on top, when I simplify this down, I end up with 5 minus x minus 5, because I got to distribute that negative. And then on the bottom, I can rewrite this as 5x times x plus 5. Just looks a little nicer. Okay, and then on top, now I can simplify this into negative x, because the 5 minus the 5 equals 0. And then I've got the 5x times x plus 5 on the bottom. But look at that, I have an x on top and on bottom. So I can cancel those out, leaving me with the limit as x approaches 0 of negative 1 on top, since there's still that negative there, over 5 times x plus 5. And now you'll see that on the bottom, I no longer have anything that would make this equal to 0 if I were to plug in x equals 0. So plugging in x equals 0, I get negative 1 over 25. Done. Okay, so those are my 4 methods for finding limits. That's all I got. Thanks for watching. Bye.